Let's look at an example of a planetary gear train now that we understand the internal and external rolling contact equations. Planetary gear trains are unique in that they have two inputs and one output, so calculating the gear ratio is a bit different than a simple gear train. Let's look at this planetary gear set I've drawn and start to label the elements. We will call the ground 1, we will call the first gear 2, the next gear will be element 3, this thick gear we will call element 4, it's a ring gear, and the arm between elements 2 and 3 we will call 5. Gear 2 is an external gear that spins on a shaft or an axle connected to the ground, and this is called the sun gear. Gear 3 is also an external gear called the planet gear. It orbits around gear 2 and is connected to a structural element called the carrier, which is also the arm of the gear system. Let's use the convention of drawing the cross-section of our gear system so that we can get a better understanding of how the gear elements interact. Let's transfer the labels over. The ground was 1, the sun gear was 2, the planet gear was 3, the ring gear was 4, and the carrier is 5. And now we can see that this shaft is a spindle because it is not fixed to the ground, it spins on it. And gear 4 and gear 2 spin on the spindle, whereas element 5, the carrier, is fixed to the spindle. And gear 3 up here spins on the carrier. Now before we get into the rolling contact equations, just as a reminder, when we talk about the angle of gears, so for example the angle of gear 2, we're referring to a vector drawn onto gear 2, so we will call this vector R2, and we reference the angle from the arm, so it would be this angle right here. So if we're talking about the angle of gear 3, we're referring to a vector R3 drawn onto gear 3 relative to the arm 5. Same with the ring gear, gear 4, a vector R4 would have an angle from the arm like this. Let's make some space on the board and we'll identify the rolling contacts and write out the rolling contact equations. The first rolling contact we have is between gear 2 and 3, and it's an external rolling contact. And the other is between 3 and 4, and that is an internal rolling contact. So the first equation is 2 rolls externally on 3 relative to arm 5, and mathematically that becomes the radius of 2 times the change in the angle of 2 relative to 5 is equal to minus, because it's external rolling contact, rho 3, the radius of 3, times delta theta 3 relative to arm 5. For this first equation, I'm going to go ahead and expand this out so we can see exactly what's going on. So we have rho 2 times delta theta 2 relative to delta theta 5. So we say minus delta theta 5 is equal to a minus rho 3 times delta theta 3 minus delta theta 5. And remember, delta theta 2 is just theta 2 minus the initial position of theta 2, we call it theta 2I. And same with delta theta 5 is just theta 5 minus theta 5I. So we're going to differentiate this equation with respect to time to get it in terms of angular velocities. So when we differentiate theta 2i, that's just a constant, so that'll become 0. Same with theta 5i will be 0. And the angle of gear 2, theta 2, will just turn into omega 2. And same with theta 5, the angular position of arm 5 will become omega 5, which is the angular velocity of 5. So if we differentiate and write it out in terms of angular velocities, we get rho 2 times omega 2 minus omega 5 is equal to negative rho 3 times omega 3 minus omega 5. That's the first equation, and now we can write out the second equation is 3 rolls internally on 4 relative to arm 5. And that becomes rho 3 delta theta 3 relative to 5 is equal to a positive, because it's an internal rolling contact, rho 4 delta theta 4 relative to 5, and we can differentiate with respect to time to put it in terms of angular velocities, and we get rho 3 times omega 3 minus omega 5 is equal to rho 4 times omega 4 minus omega 5. And that's our second equation. Let's hide our work and put our equations back up at the top. We have 2 equations describing the gear systems and 4 unknowns. Omega 2, omega 3, omega 4, and omega 5 are the unknowns. And so we have 2 degrees of freedoms, or 2 inputs. Now, depending on which elements we call our inputs and which ones we call our outputs, we'll define the gear ratio. But the entire gear system is governed by these 2 equations. Let's look at a scenario where 5 is an input driven by a motor, so omega 5, and gear 2 is fixed, so it's part of the ground. It's still an input, but omega 2 is 0. And 4 is our output, so the ring gear is our output, omega 4. Now we can solve for the gear ratio R equals omega 5 over omega 4. That's the input over the output. Equation 2 can go into equation 1, and we get rho 2 times omega 2 minus omega 5 is equal to minus rho 4 times omega 4 minus omega 5. And omega 2, we said, is 0. So this reduces down to minus rho 2 omega 5 is equal to minus rho 4 times omega 4 minus, it becomes plus rho 4 omega 5. We can move a few terms around and get rho 4 omega 4 is equal to rho 2 plus rho 4 times omega 5. Let's divide by rho 4 omega 4 to get 1 is equal to rho 2 over rho 4 plus 1 times omega 5 over omega 4. And we recognize omega 5 over omega 4 as the gear ratio, so we can finally write R is equal to omega 5 over omega 4, which is equal to 1 over rho 2 over rho 4 plus 1. So this is the gear ratio when gear 2 is fixed. The shaft and carrier are driven by a motor, and gear 4 is the output. Let's look at another case. Let's say that gear 4 is fixed, and the shaft is an input, so omega 5 in, and gear 2 is the output, omega 2 out. The gear ratio would be R is equal to omega 5 over omega 2. So real fast, we'll substitute equation 2 into 1 and get rho 2 times omega 2 minus omega 5 is equal to minus rho 4 times omega 4 minus omega 5. And this time omega 4 is equal to 0. And so we get rho 2 omega 2 minus rho 2 omega 5 is equal to rho 4 omega 5. And if we rearrange these terms, we end up getting 1 is equal to rho 4 over rho 2 plus 1 times omega 5 over omega 2, and recognize omega 5 over omega 2 is the gear ratio, and we get R is equal to omega 5 over omega 2, which is equal to 1 over rho 4 over rho 2 plus 1. And this is our gear ratio for this case. So let's look at one last scenario where gear 4 is an input, omega 4 equals an input, and gear 2 is also an input, equals in, and 5, the shaft, is an output. So omega 5 equals out. So both gear 4 and gear 2 are driven by a motor. It could be the same motor, it could be separate motors, it doesn't really matter. In this case, we're not going to solve for a gear ratio because we don't have a single output to divide by a single input. Instead, we have 2 inputs and 1 output. So what we are going to do is solve for the output as a function of the 2 inputs. So we'll combine the equations and get rho 2 times omega 2 minus omega 5 is equal to minus rho 4 times omega 4 minus omega 5. And in this case, omega 2 and omega 4 are not 0, so we get rho 2 omega 2 minus rho 2 omega 5 is equal to minus rho 4 omega 4 plus rho 4 omega 5. And we can rearrange some of the terms and get rho 2 omega 2 plus rho 4 omega 4 is equal to rho 2 plus rho 4 times omega 5. Now we can divide by the rho 2 plus rho 4 term and get omega 5 is equal to rho 2 omega 2 plus rho 4 omega 4 all over rho 2 plus rho 4. And this is the output omega 5 in terms of the 2 inputs, omega 2 and omega 4. There's a few more scenarios we could look at with this gear train, like considering gear 3 to be either an input or an output. All of the scenarios are governed by the 2 rolling contact equations. In the next example, we're going to look at an automotive differential. If you found this helpful, please click the like button and don't forget, hit subscribe so you can catch all of my latest videos.